two most common ways of doing this are through the use of a recuperator or a regenerator. This is a recuperator. It's a heat exchanger where you have the incoming combustion air and the outgoing exhaust gases flowing through it at the same time, and they're kept separate by some sort of physical barrier. It could be an array of tubes or plates, something where the two gas streams can't mingle. And the walls of the tubes or the plates are actually used as the not only as a barrier to the gases, but that's also where you transfer the heat across. And so looking at it from the combustion air blower up on the top, you have cold air coming in, passing through the recuperator, leaving it hotter than it came in. The preheated air then goes to the burner. Burner does its work in the furnace, and then your flue gases go up the stack through the other passages of the recuperator. And as those flue gases go through, some heat is extracted from them and transferred back to the next batch of incoming combustion air. And so your exhaust gas temperature decreases as your preheated air temperature increases. Regenerators have been around for a long time, but it's only been within the last 20 or 30 years that they've had a big resurrection for smaller scale operations. And the idea behind a regenerator is that you have multiples of two with all your equipment. A burner coupled with a heat storage medium. Usually it's some sort of a refractory lined chamber with something like ceramic pieces in it that are porous so that air can pass through it. And the idea is that this is essentially a storage battery for heat. And like storage batteries, if you have, for example, a portable drill at home, you know that the professionals generally have two batteries, one on the charger and one when they're using, and as soon as the one they're using gets tired, they swap it out with the one on the charger. That's essentially what we're doing here with a regenerator system. If we have reduced it to its smallest configuration, which is a pair of burners and regenerators, the cold combustion air is coming in the regenerator on the right-hand side, which has already been preheated by exhaust gases prior to this. The heated air mixes with fuel, it burns, the gases pass through the furnace, do their job, and then they're exhausted through the opposing burner, and then exhaust is conducted through the generator on the right side and gives up a lot of its heat. And so now we're preheating the medium in the right-hand or the left-hand regenerator. On a periodic basis, you reverse the system. Once the regenerator on the left side of the furnace becomes preheated to its maximum, you switch through a series of valves in the piping the cold air incoming over to the right-hand burner, light that burner, and now the flame fires across the furnace in the opposite direction, and the outgoing exhaust gases recharge the regenerator on the right side. And so what we have here is a situation where we're traveling back and forth between two regenerators, alternately charging and exhausting the heat in one of them. One of the other things that can be done very often with waste gases is not to use it as an air preheating device, but to simply preheat the load directly. And a lot of times the economics of doing this are much more favorable than preheating the combustion air. Now, what this requires in an existing piece of equipment is a footprint large enough that you can add to the length of the furnace. And this works best, of course, on continuous furnaces. What we have here is a furnace where the product travels from right to left. The direction of the flue gas flow is counter to it. You see the burner on the left and the stack, the original stack, the white one, about in the center. And that was the original furnace. And then a preheat section was added, and we closed the original stack, moved the stack down to the beginning of the preheat section. So now what we've done is expose the load to outgoing gases for a lot longer period of time and preheated the load directly rather than use a surrogate like combustion air. And this sometimes will give you better economics than using an air preheater. One of the other things you can do with exhaust from a process is to cascade it. Run process B off process A. And there are a number of ways it's done. For example, waste heat boilers are a very, very good example where steam is generated by flue gases from a furnace. Cascading does require a few things to be successful. The first is that the processes have to be in reasonably close proximity to one another, especially if you're using hot gases to transfer the heat, like flue gases. It's very, very difficult to get an economically viable system if you have to run insulated ductwork distances several hundred feet through a plant from the source to whatever the receiver is. The other important thing is these two processes have to operate on essentially the same time cycle. It's false economy to put in cascading if process B doesn't need the energy when process A is running, or if process A isn't running when process B needs it, so you have to either fire up process A and just run it as a heat source, or put auxiliary heat on process B in order to keep it working. So they work best together. And final thing is that the energy stream from process A can't be harmful to process B. Now normally we're talking hot gases, which are not a problem, but it's still something that you have to consider, particularly if you have contaminated flue gases. Now, the heating system isn't the only place where we've got to consider energy consumption, because on a lot of equipment there's a good deal of energy in the form of electricity going into motors, primarily fans and blowers, but also pumps, compressors, and any other motor-driven equipment. And there are a few rules here for getting the best out of your electrical motors. First, don't use oversized equipment and force the motor to operate at partial loads, because they're less efficient there. Where your fan loads vary widely, consider the use of variable frequency drives. Replace your older motors with more modern, high-efficiency designs. And if the equipment is used only intermittently, don't run these motors during idle times. If there's a way to shut them off and restart them when you need them, you're going to save yourself a great deal of money. The reason that variable frequency drives work on fans is that the horsepower consumed by a fan is a product of its pressure output and the flow it handles divided by its efficiency. And in this particular case, the K that we show here is just a fudge factor that allows you to go from one set of units to another. So by using a speed control on a fan, what you're really doing is lowering the pressure of the fan as the flow requirements go down. Where with most fans, where you use a valve downstream of the fan to regulate the flow, the pressure is going to stay at the full rating, even though you're only using a small amount of the flow. And so the product of pressure and flow decreases with a variable frequency drive. To sum up the things that you can do with any industrial process to try to look at energy reduction. First of all, with the flue gases, which are normally your biggest opportunity in a fuel-fired furnace, minimize the excess air or excess fuel, whatever's consistent with the product. In some cases, you will need a fair amount of excess air, and you better accept it. Make sure you get the maximum heat transfer to the load. Avoid overloading and overfiring. Limit the air infiltration. Preheat your combustion air. Consider oxygen enrichment or oxy-fuel firing, and cascading heat to a subsidiary process. For wall losses, make sure you have efficient insulation and maintain it. For opening or radiation losses, make sure that your time you have doors open is limited to the minimum necessary, and if you have any unnecessary openings, close them. With the heat to the load, you can preheat the load or hot charge it, which simply means that you're bringing the load off of one process that heats it up and putting it into the furnace before it cools down to room temperature again. That will reduce the load requirements. On your conveyor losses, you may be able to use lower mass materials for the conveyor equipment. And if it's a continuous conveyor, return it inside the furnace instead of having the return pass go outside. To reduce heat storage, use low mass insulation like ceramic fiber if you can. Schedule your equipment for 100% capacity operation as much as you can. And evaluate the merits of idling versus shutting down. And this may take some experimentation on the floor. And there's no hard and fast rule on how to do this.